Okay, once again, hello and welcome back. We are in the course on environmental bioethics within the Masters of Bioethics at St. Thomas University, and today's topic on the Hydrosphere. Beginning always with a little prayer in the name of the Father, the Son, and the Holy Spirit. O Lord, send forth your Spirit, and we shall be recreated. You shall renew the face of the earth. Amen. Okay, so just very briefly, you know how we're covering the different spheres on Earth, and they more or less follow solid, liquid, and gas, or solid, gas, and liquid, more or less, right? I say more or less because we started with the Geosphere, which at the crust is solid, and on the core is also solid. Interesting that the crust and the core, the innermost and the outermost layers of Earth, are both solid, but that in between it's liquid of different kinds, kind of a thick liquid, whether it's the outer core or the magma of the mantle. It's liquid and therefore flowing around, right? Which is also generating the plate tectonics and the continental drift. Then last lecture, we were looking at the atmosphere, this layer of gas that we have surrounding the crust of the Earth. It's a very thin layer. When we look at photographs from space onto Earth, and yet as thin as that layer is, it is a tremendous shield because it essentially burns up the vast majority of asteroids and meteorites that have been bombarding the Earth for billions of years, not million, but billions of years. And if we did not have that atmosphere, we would be looking like the moon, basically, right? Like they say, Swiss cheese, full of holes and craters. Anyway, the atmosphere is also a fluid because gases are fluids, just like liquids, but they are much thinner fluids. They're less dense. And so they fill up the entire container, wherever they are. They take up the shape of the container, we say, in contrast with liquids, which only take up the bottom of the container. And so this third lecture is going to be dedicated to the hydrosphere, or the natural liquid on Earth, which is mostly the oceans, of course, but also fresh water, natural fresh water, whether it's lakes or rivers. And we're also going to look at the ice caps with their characteristics, all in preparation for discussing with certain degree of knowledge, eventually climate change and global warming and sea level rise, all these things that are in media and in research today. All right, so we're going to look at some properties of water as such, and then some properties of water, natural water on Earth. Then the oceans, the ice caps. We're going to look at glaciers and interglacial periods, talk about statistics, the periodicity of those glacier and interglacial periods. And we'll conclude with talking about the natural right to water for humans. Going forward then, starting at the molecular level, it turns out water is this molecule. Is water a large molecule or a small molecule? Just by its chemical composition. Small. How many atoms? 3 atoms, right? Total of 3. How many elements? 2. Hydrogen and oxygen. Remember last lecture we were talking about elements and compounds and so forth. So the molecule of water is a compound in that it is made up of 2 elements, hydrogen and oxygen, and it has 2 hydrogens and 1 oxygen. So 3 atoms, 2 elements, 1 molecule. Right? The way that these hydrogens are arranged on the oxygen, they are off-center. They are not exactly at the equator. They're not opposite, totally opposite each other, but they are displaced toward one of the poles, if you will. It doesn't matter if it's the North Pole or the South Pole, depending on how the molecule is sitting, right, up or down. The point is that the hydrogens are somewhat displaced off center of the equator of the oxygen, and that gives a polarity of the water molecule, a polarity, because hydrogens have a positive value, positive charge, whereas the oxygen has a negative charge, and that makes the water molecule like a little magnet, a little microscopic magnet, okay? And so we say that water is polar. It's a very polar substance, meaning that it has a positive end and a negative end. And that makes then the water molecules stick by attraction of opposite charges. So the hydrogens of one molecule are being attracted to the negative end on the oxygen of another molecule, another water molecule. And this is a dynamic state, so they're slipping and sliding on top of each other like that. And you can see that it can be either one hydrogen or the other. So there's also the case where the molecules are flipping back and forth, and there will be a repulsion of the hydrogens from one molecule to another because positive and positive repel each other. And there will be a natural repulsion of the oxygens from two molecules, any two molecules, because negative and negative again repulse, but then an attraction by the opposite charges. So that makes water as a whole, when you think of trillions and trillions and gazillions of molecules in just in a one drop of water, all right, sliding and slipping on top of each other like that in a very dynamic state, trying to find the most stable configuration. And liquid water, which has enough energy, like I say, has enough heat between 0 and 100 degrees centigrade, right, or Celsius, to be in that liquid dynamic state moving around. We don't see it with our eyes, but it's certainly happening in any amount of liquid water, all right? And so we say that water is polar, and there is this attraction, polar attraction and repulsion of each individual molecule within the water fraction, not only among themselves, but if we add just about any object onto liquid water, or we pour liquid water on an object, or we immerse an object into liquid water, on average, those objects were going to get coated with water. They're going to get coated with water because water will stick to them naturally, all right? And that's why we say, and that's what we call hydrophilic objects, other molecules, because they like water, all right? And that's why we say that water is the almost universal solvent, because just about anything dissolves in water, almost, except for the lipids. When we talk about the organic molecules, remember the organic molecules, a review from the first course way back in the fall, that we had carbohydrates, lipids, proteins, and nucleic acids. Of those 4 groups of macromolecules, what makes up essentially all of the living organisms on Earth, right? Carbohydrates, lipids, proteins, and nucleic acids, DNA and RNA. One of those 4 categories doesn't like water. They're known as hydrophobic. But the other 3 categories love water, and they typically get coated by water. The proteins, the carbohydrates, and the nucleic acids. So which one of the 4 groups doesn't like water? The lipids, right? What's another word for lipids? Oils, greases, fats, waxes, right? They don't like water, so they're hydrophobic. We call them non-polar. But the other 3 groups are polar, meaning that they like water and they get coated with water. They become hydrated. All right, so that's one very important characteristic of water. They are these little tiny microscopic molecular magnets, and they stick to just about anything. That's why when we pour water, even on our hands, we wash our hands, and after washing our hands, what do? We shake them like this to get the hand off, to get those magnets off our skin, because skin has a lot of proteins and carbohydrates and so forth. It does have some lipids, but all that tissue gets coated with water, all right? And we literally have to shake off those magnets, the excess magnets. And then at the thin level, at the molecular level, it still doesn't come off altogether because it's a very strong attraction. So we need to use a towel to get them off. In other words, to get the magnets of water to stick to the towel instead of sticking to our skin. And that's what's happening. All right. So what we call sticky in normal language, there's no stickiness. It's all polarity. It's all magnetic polarity. All right, sticking or not sticking, but magnetically, not because of a microscopic glue of any sort. So at the microscopic level, glues are really magnets. All right, let's look at the 3 states of water in nature, because the 3 states of water in nature have a big impact on life. And we know that the water is the one that allows for the possibility of life, at least here on Earth, as we know it. Organic life depends on water, because metabolism, which when we talk about life organically, biochemically, we're talking about metabolism, right? Is essentially a soup that is reacting in an orderly fashion, and it's happening, the base of that soup is mostly water, liquid water, right? Down into the cell at the level of the cytoplasm. So we know the 3 states of water: gas, liquid, and solid. And the liquid in between is a range from 0 to 100 degrees Celsius. So water evaporates, changes state from liquid to gas at 100 degrees Celsius, or in Fahrenheit is a little more than twice, 212 Fahrenheit. So that number you see is telling us that the Fahrenheit scale is not based on water. Is based, I think it's based on mercury actually. Anyway, that's the range for Fahrenheit. The equivalent for Fahrenheit is a little over twice. Whereas on the lower end, when water freezes, right, from liquid to solid at 0 degrees Celsius, it's equivalent to 32 Fahrenheit. Positive 32, not minus 32, but positive 32 Fahrenheit, right? Okay, and when do the 2 scales meet? And you know what number they meet? So we can see by this range that the Fahrenheit scale is roughly twice as small as the centigrade scale, because we can go from 0 to 100 in Celsius, and we can go from 32 to 200, over 200 in Fahrenheit for the same temperature. Right, for the same temperature. And therefore, it's about twice the fraction, or twice the units, sorry, for Fahrenheit than for centigrade, approximately, but it's not linear. So the 2 scales meet, just out of curiosity, when it's the same number of centigrade and Fahrenheit, or Celsius and Fahrenheit. Anybody know that? Just curiosity. It's below, right? It's minus, and it's minus 40. So minus 40 centigrade is equal to minus 40 Fahrenheit. That's where they meet. And minus 40 centigrade and minus 40 Fahrenheit, same number, right? And then as we go up, the scale rises about twice as fast for Fahrenheit than centigrade. Anyway, just curiosity. One thing that is very important for nature is this phenomenon here. The change of state from solid to liquid to gas of water, pure water. This is what happens. There's a different configuration of the molecules. First, let's begin with the gas. In gas state, the molecules essentially are dissociated. They're bouncing off of each other. And the reason for this is because there's what? There's either high heat, again, above 100 degrees centigrade, or we can reach the equivalent by doing what? By releasing the pressure, all right? By having less than the atmospheric pressure. So either high heat or less pressure. What happens there is that the molecules become dissociated with each other, and they are essentially in a dynamic state, bouncing off of each other very, very fast, but they don't stick. They don't stick because extra energy has been applied. The extra energy either by heat or actually by generating, going toward a vacuum or getting rid of pressure, all right? So now we go from gas to liquid. We are either taking heat out of the container to liquefy the water vapor. You can think of water vapor. We're either taking heat out, it's a process called condensation, or we can exert pressure, alternative. Putting pressure on will start bringing the molecules together, right? And so we transition from one state to another into liquid. And now the molecules in the liquid state, it turns out that the molecules in the liquid state are slipping around each other and sliding, but because of that attraction, because of that magnetic attraction, right, they actually cluster, form a bigger density, form a higher density than in the solid state. So that when we transition again from liquid to solid, and we can do that in two ways, we either do what? We continue to take out heat from the container, right? In other words, we go below 0 degrees centigrade, below 0 Celsius or 32 Fahrenheit. How can we do that? Very easily. We put the glass of water where? In the freezer, right? We put the glass of water in the freezer and it will freeze. But be careful, because if that glass of water is either plastic or glass, what's going to happen to it? It will crack. It will crack. And you won't notice until you thaw out the water, but it's very dangerous. So never ever put glass of liquid in the freezer. For example, chilling the wine, very dangerous, because that could explode, all right? This is what happens. It turns out that when water becomes solid, essentially it crystallizes, and we're talking about pure water, of course. When it crystallizes, look at the crystalline formation. The crystalline formation is a homogeneous formation whereby, you know, every atom is in the right place with regards to hydrogen and oxygen, all right? And therefore, when water does that, it actually expands slightly. It expands slightly, all right? From liquid to solid. It's a characteristic of water. It's a very powerful characteristic because then it's going to cause erosion in nature. And you'll see over periods of time, long periods of time, thousands or millions of years, it would actually crumble mountains down to rubble, all right? So I never knew about this phenomenon. And as a kid, I always got scolded because of this phenomenon. And this is what I'm trying to say. When I was a kid, I was in charge of making ice in the house, okay? So my mother taught me to fill the ice tray. And at that time, they were even, and they weren't even plastic, they were aluminum ice trays. I'm ancient, I'm from last century, from last millennium. And we had these aluminum ice trays, you find them in museums today. Sorry? We still have them in Cuba, of course, because Cuba has become a national museum. All right. So remember these trays? You can probably still buy them and start your own museum. But basically the idea is that you fill the ice tray with water, right? And you lower the lever, lower this lever and put the thing into the freezer and let the water freeze, and then you pull it out a little while later, and maybe you run some tap water on top of it to get all the ice crust off, and then you pull on the lever, and the lever is supposed to pivot this little, is supposed to pivot these levers here, okay? And so that the ice becomes loose, the ice cubes become loose. The problem is that I would fill the thing to the rim, like my mother taught me, put it in the freezer and then take it out when it was frozen, and the whole machine was frozen over, all right? And so eventually I ended up breaking the aluminum lever from trying to open the thing because it was all frozen over. And I would get a scolding. And I would say, but Mom, I filled it to the rim like you told me to. And the whole machine now is all frozen over and it's not my fault. And my mother said, well, go do it again. You know, so I would pay more attention. And so obviously my mother didn't know about this either, that water expands when it freezes. And I would go and very carefully fill it to the brim again. And sure enough, the same thing kept happening again and again. So at some point, thanks be to God, these plastic ice trays came out, right? Or rubber, I should say. So they're elastic. And that's the reason for making these rubber ice trays, because at some point, some scientists figure out, or engineers, whatever, they figure out that water does expand when it freezes. And so the rubber will take up the expansion. But the problem with the other ones was, is that when water expanded in freezing, it would actually cover the top of the machinery here and freeze everything solid, right? And the ice would actually build up outside, above the rim. And I just couldn't figure it out because I was very careful to fill it to the rim, and then invariably the ice would go on top of it. Well, it was decades later in a science course that I learned this phenomenon, that water actually expands. And so if the container is rigid, it will crack the container, because water also has a characteristic that it is what we call essentially incompressible in its liquid and solid state, all right? So you can actually put entire buildings on top of water or liquid or solid water, and the water will not compress. That is also a characteristic that is used in seismic areas where the earth shakes, all right? They literally construct buildings. The foundation of buildings are sitting on top of a water tray, a gigantic water tray, so that when there's an earthquake, that water, liquid water, takes the vibration, you know, and absorbs the vibration of the tremor and doesn't transmit it to the actual building itself. I know that in Mexico, we lived in Mexico City, and a number of buildings, high rises in Mexico City, the foundations are literally sunk into, there's floating on top of water, liquid water, because water is also incompressible, all right, liquid and solid water. So it's a very powerful agent of erosion, like I'll show you in a few minutes with regards to natural phenomena on Earth, okay? And that is also why, so which one do you think is more dense, liquid or solid water? Again, if you look at the structure, there will be more water molecules in this circle of liquid, this sphere of liquid, than in this sphere of solid water, okay? And so liquid water is more dense, has more water molecules per volume than ice. And that is why ice floats on water, on liquid water, all right, because it is less dense, all right? That's one reason. Another reason why icebergs float is also because they have a lot of air particles inside. That's a separate story. But if it was just solid water, like an ice cube on a drink or a refreshment, floats because the crystal structure of water, the solid state, is less dense, somewhat less dense than the liquid. All right. Okay, so these are properties of water that have an impact on nature in a very dynamic way. Forward. Let's look at the specific heat. This is another characteristic of water that also affects nature. It turns out that water retains heat, just like CO2 retains heat. We mentioned that, carbon dioxide. Okay, water also retains heat in all three states, but particularly the liquid phase retains heat quite a bit. And so that's what is called the specific heat of water, the specific heat, which is almost 4.2 joules. That's the units of specific heat, all right? 4.2 joules. It's the amount of temperature that it takes to raise the temperature of water, all right, 1 degree Celsius. And so it takes that amount of heat. To contrast it, for example, to raise copper 1 degree Celsius takes only 0.4, like 1/10 joules of heat. Copper, all right? And that's why copper also transmits heat very easily, and that's why the bottom of pans, of cooking pans, sometimes have a plate of copper because it diffuses, it transmits the heat very fast. So it takes 10 times more heat energy to heat water than to heat, for example, copper, a metal, which occurs solid in its natural state. That means that water retains a lot of heat, all right, before it reacts, let's say, to that heat, all right? And so that's also important when we talk about atmosphere. It means basically, and also oceans and even fresh water, it means that whenever there is water around or humidity, it tends to dampen the heat amount. So that cities, for example, that are near oceans or near lakes, in the winter, they will be slightly warmer, and in the summer, they will be slightly cooler because the water body next to them absorbs heat. The same argument can be made with the atmosphere. If there's more humidity, we feel more heat because that humidity is holding to heat. Whereas if it's dry, less humidity, then we feel less heat. I was mentioning yesterday that we were working in the forest with the team of the summer research students. It was getting very hot out there toward noon because it was very humid. The atmosphere was loaded with gas, water, with humidity. And so it felt warmer. We were sweating bullets because the humidity was holding on to heat. I was saying that if we were in the same place, but there would be less humidity, it would be dry, like a desert, for example, all right? We would feel hot in the sun, but we would actually feel cool in the shade. In the desert, we will feel cool in the shade because there's practically no humidity. So there's no heat that is sticking to our bodies because of the heat retention of water, all right? So water retains heat, and that has an effect on the atmosphere and the hydrosphere on the living systems that live there. It also affects the wind patterns, and we saw in the previous class of the Hadley cells and how they form, the three major sets of Hadley cells, the tropical Hadley cells around the equator up to about 30-degree latitude, north and south, right? And then the temperate cell, or band, if you will, in the temperate region from about 30 to 60 degrees, north and south. This is latitude. And then the final set of cells, the Hadley cells, are polar. either on the north or the south pole, from about 60 to 90 degrees north or south, all right? Again, because of the amount of heat that is in the atmosphere, which has to do with the angle of incidence that we talked about in the previous lecture. And so you see how one concept is helping to understand the other concept. This will then, these cells will have an effect on the ocean currents, and the ocean currents themselves will also have an effect on the atmosphere. So it's a dynamic state going back and forth. That basically regulates the annual, what is known as the annual mean temperature, so that in the tropics, that annual mean temperature fluctuates less, and it fluctuates more in the temperate region, in the middle cell of the temperate region between 30 and 60 north and south. And again, it fluctuates less again in the polar regions. Okay, let's continue. So I mentioned the crystalline structure of water. Again, here it is shown. This is in the liquid state. It tries to fill in as many gaps as possible. You can see the hydrogens and the oxygens interacting here, back and forth in a dynamic state. But in a crystalline state, energy has been withdrawn from the system, right? Heat has been taken out of the system, and therefore the molecules are going to try to arrange in the most stable form when there is least motion, okay? And therefore the crystalline structure is going to be larger, less dense than the liquid structure, thus forming crystals, expanding. And what are these? These are snowflakes. That when we look at snowflakes at the macroscopic level, we will see a crystalline pattern, a crystalline structure, which typically is geometric, of many different shapes. Why? Well, because snow is not pure water, all right? It has some contaminants in it, little tiny particles, dust, whatever, and that accounts for the different types of crystalline structure that we see, different types of snowflakes, different shapes of snowflakes. But if we had pure water, it would be a single type of crystalline structure, all right? Because each pure element, when it crystallizes, has a particular pattern. That, by the way, is used in X-ray diffraction to find out what that pattern is, and then use that pattern to determine an anonymous element, to see what element it is by comparing the crystalline structure or the X-ray diffraction pattern of that crystalline structure. So moving forward, here is the natural consequence of this water, freezing and thawing is going to cause vast erosion on water, on not only on rock, all right? But there are two types of erosion, and it's important not to get them confused. One erosion is by the freezing and thawing of water over year after year, season after year, from winter to summer, right? And so here's a very graphic example. This is a diagram, of course, a caricature of how it happens. Water gets in there during the summer, the rainy season. And then when it freezes in the winter, it actually expands and cracks the rock. And you can see here, this boulder has been cracked in 3 places. So this boulder has been fragmented into 4 segments over time. And so if we fast forward this more and more seasons of freezing and thawing, the expectation is that this boulder will eventually be cracked down into rubble, all right? And you can take this argument all the way down to the microscopic level. So water is a very powerful erosion agent in the temperate region where water goes from liquid to solid on a yearly basis, to follow, and back to liquid. However, in other regions, water causes a different type of erosion, which is by running water. This is liquid water. And it could be either a river, like in the Grand Canyon, right? This erosion is through a river going through a platform, going through a plain. So these are not mountains, this is not rising, but this is digging down through the layers of sediment. There's an estimated 1 to 2 miles of sediment in the Great Plains, in the mid-region of the US, right? The Midwest, precisely where the Grand Canyon is. So this is going down from the layer of sediment over millions of years, the erosion of river carrying away sediment from the sides, from either bank of the river, okay? And that is emptied out typically to an ocean, and then it generates what is known as a delta. When the river breaks up at the shoreline and expands out, and it's called a delta. And then all that sediment is being deposited out into the ocean. So for example, the Gulf of Mexico, which has a number of rivers coming into it, including the Mississippi, the mighty Mississippi, right, has been dumping sediment into the Gulf of Mexico for millions of years. And so the Gulf of Mexico tends to be more shallow than other seas because of the amount of sedimentation that has been dumped there from the Great Plains, from the Midwest. Different is a glacier, which is now solid water, but it's also moving and grinding back and forth as the glaciers. What the glaciers do is they expand and recede with the different seasons, and they are also grinding underneath, and it's a very powerful erosion agent. It's essentially like a humongous sandpaper that is scraping the base of the mountain range wherever the glacier is flowing. And you can think of it as a solid river of huge chunks of ice that are expanding and receding periodically, again, over long periods of time, and they're grinding mostly the bottom down to sand and very fine sediment. Okay, so that's a glacier erosion that can also generate mountains. Okay, let's move forward. Here is an example of a diagram of how a river matures and goes through different stages. A young river typically is fairly straight. The flow is fairly straight. And as the river matures with time, what happens is that the river starts meandering, right? Again, finding the path of least resistance. The river will flow generally in the direction of gravity, right? Gravitational pull, so from a high area to a low area. Whether that river empties out into the ocean or into a lake, it depends where it is geographically on Earth, on the crust, right? However, that water, that liquid water of the river is always trying to find the path of least resistance, which is not always a straight line. It will be kind of a straight line at the beginning of the flow of the river simply because of the impetus of the water itself. But after a while, that river is going to start looking, or the water will start meandering back and forth, following the path of least resistance. What does that mean? Where the sediment is less dense, more loose, that can dislodge easier, and yes, mix in with the water, and then be taken, or that sediment be taken downriver, all right? And as the river meanders, it tends to meander even more. So now you can see when the river curves, it is going to erode more the outside of the curve than the inside of the curve. In fact, there's a phenomenon that happens here. It's kind of synergistic. The more that a river meanders, the more that it tends to meander off center, all right, laterally to the sides, and it keeps expanding laterally. You think about it, especially if it's basically soil on silt or sand, because what happens is that curvature, now on the outside of the curvature is eroding there, is digging out sediment or sand or soil, right? Dissolving it, whatever is dissolved, into the water or just carrying it downriver. Conversely, on the inside of the bend, the river tends to deposit sand or soil or silt, right? And so this bump continues to push out, if you will, or grow out, whereas the curve continues to dig laterally, sideways. And so an old river zigzags a lot. And sometimes it zigzags so much that other bends, inner bends, get eroded away and connect. And they end up forming islands, because at some point when this connects here, then you're going to get a new flow of the river through here. All right? And it will generate an island. That happens with very old rivers. As you see, it has these pockets or vestiges of the original flow. And at some point, when the river meanders sideways enough, it would actually redirect its current flow, all right? And will start the whole process again. So it can rejuvenate itself, starting the whole process, but at a deeper layer of the sediment. And it will go through another layer. And that's in part why that erosion, that river erosion, you can see it's layered horizontally, because it all depends on the sediment that is there, if it's offering more or less resistance to the water flow, all right? And so the contour, the shape of the canyon will actually be revealing the density of the layers of soil or sediment that the river has gone through. And whenever there is a crevice going into the canyon, unlike something like that, we can pretty much say that that was an area of least resistance, where the sediment was somewhat loose, more loose for the river to take that out. It was one of the bends of the river, if you will. And you can follow that argument all the way down, so you can tell more or less what the flow was at the top of the canyon in contrast to the bottom, depending on what kind of density of sedimentation it found, the river found, as it was bearing down into the canyon. All right, so interesting dynamics for rivers. It also it shows graphically that the river is not a static flow of water, but very dynamic, not only in the flow of water itself, which can also vary from season to season. Typically, many rivers are fed by melting ice or melting snow. So if there's more snow or less snow, depends on the season of the year. Some rivers actually dry out in the winter because there's no flow of water, because the snow is accumulating, or the ice. And then in the spring, when all that ice and snow melts, it comes down the river and there's a flow in the river. And all of a sudden, life starts appearing inside the river. Not only plants, which is understandable because it could be seeds or shoots that are, or little part of the vegetation buried on the ground, on the bottom of the river, but also animal life comes out. And not only amphibian, but actual fish. So some eggs, fish eggs, can withstand a dry season, and they'll come back up. They'll hatch when the river fills with water. All right. So river flow is very significant for life on Earth. All right. Another characteristic of water and the physical chemical characteristics of water, we talked about its crystallization process. We talked about the heat capacity, the high heat capacity. I want to talk now about what is known as surface tension. The surface tension is, again, the amount of heat that it takes to release one molecule of water at the surface to go into gaseous state. All right. Now, it's also important to understand that on any surface, but particularly the surface of water, some molecules are being released into the atmosphere to go into a gaseous state, and other molecules are coming in, are being trapped into the liquid phase, again, mostly by that molecular attraction. And so there is also a dynamic interaction, interchange of molecules of water at the surface, going from liquid to gas, back and forth, all right? And on average, if we maintain the temperature steady, again, between 0 and 100 Celsius, there will be an equivalency where more or less molecules are leaving, or going from one state to another. But typically, there's a balance. Equal number of molecules are leaving, are going from liquid to gas, than are going from gas into liquid. And so the net result is a stable number, all right? But it takes energy, I said, it takes some energy, some heat energy to leave the surface, all right? And that's called surface tension. Surface tension. Different liquids have different surface tension. It turns out that water has one of the highest surface tension per density, per molecular structure, you know, per size, etc. So the surface tension of water is again important in many aspects of nature because it's part of what makes that water stick around, and it also allows a number of animals to actually live on top of water and walk around on top of water literally, as long as they don't break that surface tension. Here is an animal, I think it's called a water strider. Water strider is a type of insect, okay? And this guy actually kind of rolls on top, or literally walks on top of the surface of the water. As you can see here, the surface tension is being bent in, but it doesn't break. So as long as this creature doesn't break the surface tension with its legs, it will not sink and it will not drown. It can literally walk on water, all right? What we don't see here is that the distal end of the legs, the last segment here, has little tiny hairs, literally microscopic hairs called setae, and those setae increase the surface of the legs immensely, all right? So it's the difference between having, let's say, just a cylinder or having a cylinder with spikes coming out all around it. The spikes will increase the surface, the amount of surface on that cylinder, all right? And that's at the microscopic level, and that's what the legs are doing here. They have all these little tiny hairs that increase the surface tremendously so that they don't break the tension. We can do a similar experiment artificially if you take a paper clip, and just place it horizontally, very carefully, on top of water. Take a glass of water, fill it close to the rim, all right? Don't freeze it or put it in the freezer. Just take a glass of liquid water and fill it close to the rim. And then take 2 paper clips. One paper clip you leave alone, and the other paper clip you unfold to make kind of like a little grip, all right? Make like a kind of a little forklift out of it. And then with that forklift, lower the other paper clip horizontally, very slowly on top of the water. And you can literally rest that paper clip on top of the water if you do it very slowly. Because what's happening is that the paper clip is light enough so it doesn't break the surface tension. Then what you can do is you can disrupt the surface tension. You drop a little drop of alcohol, for example, on the surface. You drop a little drop of alcohol away from the clip, and as that alcohol diffuses on the surface, it will break the surface tension. It will change the surface tension and the clip will sink. So you can do that with your kid siblings to impress them that you know how to do magic. Make clips float on water and then make them sink. All right, so those are simple little experiments, but it's all about the high surface tension that water has, all right? Part of what makes the water also stick, you see how the water beads up and it makes a concavity, right? This is it's called the meniscus, and the meniscus bends in, so that's a negative meniscus. If it bent out, then it's a positive meniscus. Anyway, water beads up on other surfaces, because of its surface tension. It also, you see the swimmer, right? It's just above, she hasn't broken the surface tension yet. So the water, there's a film of water, very thin film of water that is actually traveling above her face, right? And it's a bulge of water because of the surface tension hasn't been broken yet. Interesting. So very interesting dynamics of the surface tension of water, relatively high, that actually allows creatures to move about. There's also a lizard that lives in South America, in Central America. We have them here in the forest, okay, the slash pine forest. What are the lizards called? Well, we used to call them in Central America. I used to live in Guatemala for a while. They're called cutetes. Let me see if it shows up as cutete. But it's just that, yeah, they're basilids, all right? You may see these lizards around in our forest. They're invasive. They have this top thing here. It's kind of a heat dissipator for the brain. And they're very fast runners. They're very fast runners. Here you go. Oh, wow. So the cutete can actually run on water. Not working. Okay, well, you can look it up later. The thing is that these basilids, where are we? The basilids literally can run on top of water. They're so fast, they get up on their hind legs, just like you can see here. Okay. But what it is that they have the same little thing. It's called a parallel evolution. They develop the same as a water strider, little tiny hairs or setae, hair-like structures on their digits, on their on their toes, okay, the lower legs. And so it causes the same thing. It increases the surface area of the toes. And so they're also very fast on their hind legs, and they can literally run. They don't walk. If they were to walk, they would sink because they're taking too much time. But if they run, they can run across a stream or lake. I've seen them run across a stream or lake or river when we chase them and try to catch them. Basilids. Okay. So surface tension also affects nature relative to water. Erosion is also very strong on the ocean, at the shoreline, okay? Whether it's sandy, if it's sandy, it's going to be high impact, mostly by currents, oceanic currents, or the tide moving in and out, but more the current itself, so that it causes a lot of erosion. Also, the impact of waves will be a high erosion mechanism. And what are these? Anyone know? These are the famous hills of Dover, or the cliffs of Dover, the white cliffs of Dover, if you have ever heard that phrase. They can actually be seen rarely on a clear day from the coast of Normandy, which is northern France, right? Let's see. There we go. It's a famous, there are even poems about this. What I want to show is actually a little Google map here, satellite image, because it's the Strait of the British Isles. This is the North Atlantic. Get situated. Here's Florida, Miami. All right, we go across the North Atlantic. Here's the Mid-Atlantic Ridge, remember? So this is minus the water column. And we go into the British Isles, UK, Ireland. And then here is France, Belgium. This is significant. Anyway, this passage here is pretty rough because it's the English Channel, right? And those cliffs of Dover can be seen on a clear day from the French coast, looking northwest to Great Britain, all right? And this is significant when during the Second World War, this is Calais, Dunkirk, all these beaches here. What happened on these beaches in 1945 was D-Day, right? The invasion of, because France at that time was under Nazi domination, and there was the famous D-Day of the Allied forces going into France, into continental Europe to defeat Hitler, all right? And so they were lining up over here at the cliffs of Dover, the Allied forces and all the invasion that came, also with air support, et cetera, et cetera. But that erosion, which is pretty significant, as here you can see the scale. This is a lighthouse, for example, has been done by the ocean and continues to erode. So periodically another segment is mostly chalk, right? And periodically another segment of the wall falls in. Mm-hmm. Anyway, closer to home here, we have the coast in the tropics mostly, where we have mangrove plants growing on the shoreline, on sand, sandy sediment. And this is important because the mangrove has these aerial roots. Mangrove is a very interesting plant that literally grows in salt water. So it has a mechanism on the roots, on the root system, that literally sucks pure water out of ocean water, all right? Out of salt water, the mangrove roots literally suck pure H2O out of the seawater, and it's a mechanism called active transport. And that active transport, excuse me a minute, I just want to bring it forward. Where is bring forward? Yeah, bring forward. There. Talk about the root system, should be visible. Yes. These, of course, here is low tide, right? But when it's high tide, this is all flooded with ocean, with seawater, and very few plants actually are able to live and tolerate salt water, right? Because salt water dehydrates. But they have what is known as an active transport system, and it causes the mangrove plant energy, an investment of energy on the cells, the hairs, the root hairs, to absorb pure H2O out of salt water. The plant has to invest energy, and to do that is a system called active transport. However, that adaptation allows the mangrove to grow where no other plant can grow, which is the shoreline. And by doing that, then it has no competition for sunlight, and through photosynthesis, it makes an excess amount of glucose, of course. So the mangrove has plenty of energy to spare in the root system in order to survive in that environment, all right? Another plant that has adapted that way is some types of grasses that are associated with lawn grass. It's just the lawn, the grass that we have on the lawn, all right? It's called Falacia, and that grass grows on Biscayne Bay, for example. And when there is that grass growing on Biscayne Bay, that is a sign of a healthy bay. We have a problem with Biscayne Bay because it's these patches of grass are disappearing. And so when that becomes barren, see this underwater grass growing on salt water, you can see that it actually looks very similar to lawn grass, right? It's a long blade like that. That's a sign of a healthy environment. But when you start getting patches like that, sandy, then that's this is Virginia Beach, actually. Recognize it from the little sculpture that they have there. And these little jetties are to prevent erosion. As you can see, which way you can tell, it's very informative, this photograph, which way is the water flowing. This is Bear Cut going on Key Biscayne from Virginia Key to Key Biscayne itself on the bridge, on the second bridge. Okay, across from this is the Rosenstiel School of Marine and Atmospheric Science. Next to this is the NOAA station, NOAA. Anyway, you can tell that the flow of, the general flow of the current is this way because of the way the jetty, because of the sand, how it's accumulating, eroding here and depositing on this side, right? And here where the jetty is broken, then is more flat, but it's missing grass. And so that is an ill health. It's important to have the grass because it stabilizes the coast. When the grass or the mangrove leaves, then we get erosion like it's shown here. See, there's no mangrove in here, so there's erosion of the beach, right? The current, slowly but surely, will take away the sediment on the shoreline and will continue to dig in, and we're losing shoreline. We're losing shoreline to the ocean because of erosion. So now mangrove finally is protected by law, and therefore, because it's a stabilizer of the shoreline. Okay, let's see. It's almost 11. I wonder if this is a good spot for taking a break. How are people doing? We'll take a little break or continue. We have about 5 more slides to go. So we're about 2/3 of the way of the presentation. Why don't we take a little break now? All right, 10 minutes. And we'll start up again at 11. Okay, so it's about 10:50 more or less. We'll stop here with salinity. I'm gonna pause the recording and we'll come back at 11, all right? Here we go. Okay, everyone, welcome back. Going to the second half here. Okay, we left off with another characteristic of water, which is its salinity, or the chemical composition of water. This again has to do with its polarity, the fact that water is so polar, right? It's this little molecular magnet that it is known as the almost universal solvent. Vast majority of substances dissolve in water. And by the way, whatever doesn't dissolve in water will dissolve in alcohol. The lipids, the hydrophobic substances, will dissolve in alcohol, and then alcohol will dissolve in water. So that mixture, if you want to get oil into water, one back way of doing it, roundabout way, is dissolve that oil into alcohol, and then that mixture you can dissolve into water, because then the water will coat the alcohol that has the oil attached to it. Okay, so back to the chemical composition of water itself, of natural water, whether it's fresh water or salt water, or in between what we call brackish water. All right, so example of fresh water will be either rivers or lakes or ponds or swamps. And then brackish water will be the estuaries or deltas of river, where you have precisely freshwater runoff into the ocean. And the mixture that happens there, mostly because of tides, the tide coming in and out, ebbing and flowing, which will mix that water somewhat. That's called brackish water, And then ocean water, whether it's an actual ocean or a sea or a gulf, right? But basically salt water. So there's a salt water range. And this, again, is measured in parts per thousand. Parts per thousand, as we saw for the amount of CO2 in the atmosphere. That scale was actually parts per million, right? 400 ppm. So in the amount of salinity of water is measured in ppt. So fresh water, for example, has a very low salinity, 0.5 ppt. All right. If we were to convert this to a percentage, because it's parts per thousand, we would have to add another significant zero. Significant zero is going to be to the right of the decimal, not to the left. So it would be 0.05%, right? Or pph, if you want to call it parts per hundred, 0.05. Or, but the scale is much easier because it gets you into whole numbers, into the range of whole numbers. So ppt is a standard unit of measurement of salinity of the ocean, parts per thousand. If ever you've maintained a saltwater aquarium, you know that the hygrometer has to be in this range here. About 35 is the average parts per thousand ppt of salt water, right? Those salts are made up of chemicals, either anions or cations, depending on the charge, but these are essentially minerals. And there's an average of about a dozen minerals that make up salt water. So it's not just sodium chloride. You see chlorine is here, sodium, natrium, Na, from its Latin name, natrium, all right? Sodium is a positive ion or cation. Chlorine is the negative ion or anion. Together, NaCl is a chemical formula for table salt, right? Sodium chloride, table salt. That's two of the minerals, but there's about a dozen minerals that form seawater, all right? A dozen minerals that are dissolved in it. And as I mentioned, the average ocean water ppt is about 35. The range is 32 to 37, to get that. When it's brackish water or estuary, it's anywhere from half to 17, right? That's the brackish water, kind of in between, you see, 17, about half of 35, 16, 17. Then you have two extremes with regards to oceans. The Black Sea, that because the Black Sea is enclosed, and then what happens, actually not enclosed, the Black Sea is surrounded by mountains, so the salinity of the Black Sea is being replaced by fresh water, basically. It's being dissolved out. So the Black Sea has very little salinity, about half the average of ocean water, right? The Black Sea, show you a map in a minute. In contrast to that, the other extreme is the Dead Sea, which has about 10 times more salinity than the ocean, 10 times, okay? That has an impact on density, So this is a little slide that I just put together to show water density. If we use tap water, which is mostly fresh water, right? Has very few minerals by comparison to salt water. So tap water is actually more dense in the sense that there are more water molecules per volume. Another way of looking at this is that the more salt you add, the fewer water molecules per volume, all right, for the same volume. So think about it again. The more salts you add, the more minerals you add to water, the less water molecules per unit volume, because the water molecules are being displaced, if you will, by the mineral molecules. So water becomes less dense. And that's why things float in salt water more than they do in fresh water. In fact, if you swim and you swim in a pool, you swim lower than the surface in a pool. It's a freshwater pool. When you swim in the ocean, it's a little higher because of the density, okay? The minerals give more buoyancy. And so here's a dramatic example in the ocean, in the sea, we float more. It's because of the salt content. And the most dramatic example is in the Dead Sea, actually, where people float on the whole top side. If you're floating on your back, the whole front side of your body is out of the water, literally. So you can float like a raft, okay? And people can read the newspaper or take notes or write letters, whatever, on the Dead Sea as they're floating because their top body is totally out of the water. Literally, you can see a photo here, okay? So we would expect the opposite in the Black Sea. Let me go there for a moment. For example, just geographically to locate, it's in the Balkans. Belongs to Russia. There's the Black Sea. And it opens up, I think actually to the Straits of Bosphorus, no? The Bosphorus Strait. We'll get to the map. Nope. Give me a minute. Let me go back here. Because these are satellite images. I was trying to find the Google Earth thing. Where was the Google Earth? Let's try map. Okay, well, here's one. Yeah, the Bosphorus Strait is here, which is a natural opening. And this is Turkey. So that's the Istanbul, the city of Istanbul is there. Used to be Byzantium. And so the Black Sea, because it has a very narrow opening to the ocean, this would open to the Mediterranean, okay? And it's surrounded by mountains, then the mountains are constantly dumping fresh water into the Dead Sea, and they are replacing the salinity to the point that the Black Sea is now only half as salty as the average for the ocean. Okay. It's becoming brackish. Be interesting to see the fish in there, how they have adapted, because this is a very slow natural process. Something like this happened a little more drastically in some lakes that are in Nicaragua, the Blue Lake and Green Lake, Nicaragua. And what happened there was pretty dramatic for the fish in there. Blue and I think they're called Green Lakes. Nicaragua. Right. And in these lakes, well, the isthmus was not there. It came up from the bottom of the ocean. And originally this was salt water, and it trapped fish in there. And then over thousands and thousands of years from rainwater, the salinity was worn out, run off. So now they're freshwater, and many of the fish, the original saltwater fish died, but some of the fish survived, and significantly sharks survived. And now these are freshwater shark, some species, and there are some of the more aggressive freshwater sharks that have survived in these lakes. All right, so one has to be careful with the rivers that are feeding off, because those sharks sometimes get into the rivers and they get lost in those rivers, and people take their cattle into the river. They can get attacked by the shark in a river. Right? It's freshwater. So these sharks have actually adapted over eons to the freshwater. It's a process that they, through their gill system, they're able to process the freshwater. Anyway, that has an impact. The salinity of the ocean has an impact on life, whether it's freshwater or saltwater marine life, right? And it's because of these dozen minerals that are dissolved in the water column. Let me shift back into the big picture of the ocean currents, the oceanic currents. Here, similar to the atmosphere, where we have a combination of the two currents, the Coriolis and the convection currents that make up for the wind pattern. We have something similar with the ocean, but a little different because the general motion is more horizontal than vertical. The wind patterns on the atmosphere tend to be this vertical and slanted sideways, so diagonal combination between the vertical convection current and the diagonal Coriolis effect, right? That makes for the wind patterns and the Hadley cells on the surface of the Earth and the atmosphere. The currents on the ocean are a combination of the convection current that occurs in the ocean itself as the water, the surface water, the sinking and the rising there, but also the more affected by Coriolis sideways. But the difference is this: since liquid water, so the oceans are liquid water, right? Then they take up the shape of the container, but the bottom of the container, which is essentially the ocean floor throughout the entire surface of the Earth, okay? And therefore, they're more affected by the Coriolis laterally, and it generates these gyres, what are called gyres. And so we have 5 main gyres on the planet. There are 2 on the northern hemisphere and 3 on the southern hemisphere. So in the northern hemisphere, we have the North Atlantic gyre that you can see here basically rotates clockwise, and it's moving warm water, beginning with the tropics near the equator, up through the Caribbean and continues north and catching with the Gulf of Mexico, right, with the Gulf Current. And then it moves across the North Atlantic into Ireland, the British Isles and Ireland, but this is Ireland over here. And what happens is it dumps warmer weather because on top of the ocean currents, there are also going to be wind currents, wind patterns that are following basically the ocean currents. For example, on any given day, if we have blue sky above and you look toward the east in Miami or along South Florida in general, on any given day, if we have blue skies above and we face east where the ocean is, where the Atlantic is, we will see a swath of white clouds, typically cumulus clouds. All right, those white clouds are generally on top of the Gulf Stream. So we can tell without seeing the Gulf Stream directly, miles inland, we can tell where the Gulf Stream is in general because of the cumulus clouds that are hovering above. See, that's warm water that is evaporating and moving up into the troposphere, right? And now it's water vapor, and they're slowly moving with the current northward. So the general pattern of the breeze that we get in South Florida is a breeze from the southeast coming like this toward the northwest. It's a diagonal breeze. That's the general pattern from the southeast to the northwest, approximately. And so when that breeze becomes strong enough, it will blow those clouds inland and we get precipitation, we get rain. Alternative, the clouds will coming in from the Gulf Coast into the peninsula and we get rain also. But so you see that cloud formation that is hovering above the Gulf Stream and will eventually move into the mid-Atlantic, the North Atlantic, and cross over to Ireland. And that's why Ireland is a little warmer than it should be by latitude. So Ireland should be colder by latitude, but it's warmer because the Gulf Stream ends up dumping its humidity over there. And then as it does that, Gulf Stream gets cooled down by Arctic cold water circulation. Some of it comes down the coast. And so the coast of Portugal, for example, is on Western Europe, is a little cooler than what it's supposed to be by latitude, because it's receiving that cold current coming downward towards the tropics, similar to the California current, which is colder than what the California coast and the Baja California Peninsula should be, because it's picking up cold water coming from the north, coming down, sinking down into the equator. There at the equator, it gets warmed up again, and it continues to flow in that clockwise fashion. That's the North Atlantic Gyre, G-Y-R-E, all right? In the South Atlantic, we get a similar effect, but in the opposite direction. Again, the current south of the equator is going to flow from east to west. And when it gets to the coast of South America, mostly the tip of Venezuela and mostly Brazil, actually, not Venezuela, Brazil. It's all Brazil here. And it's going to cause a southward gyre that is going to be counterclockwise. And then when this current comes down to Antarctica, it's going to get very cold down there and pick up some of the cold water from the Antarctic and move it northward, coming north on the coast, the west coast of Africa. As it goes to the equator, we'll warm up again and we'll continue that cycling, but that's a horizontal cycling. So that would generate another gyre that is called the South Atlantic Gyre, all right? Then on the Pacific, we have a similar effect, but much bigger, because the surface of the Pacific is much larger than the surface of the Atlantic. In fact, the volume also. That's why the Pacific has 2 tides per day, as opposed to 1 tide on the Atlantic, okay? Because the Pacific, by comparison, is much larger than the Atlantic. At any rate, we get a North Pacific gyre that is again going to be clockwise, and we get a South Pacific gyre that is counterclockwise. And the North Pacific, by the way, is the most significant one. There's accumulation of garbage, right? They're called the Great Gyre Garbage Patches, the garbage passes, floating stuff, mostly plastic. There's also wood and other stuff that floats, but it's mostly plastic that is floating, and it accumulates kind of toward the center of the gyre, or it rotates around, right? But there is what is known as a great garbage patch of the North Pacific hanging around here, but you won't see it too much because it's dispersed. So it's not a big island of plastic where one can literally walk onto, right? No, it's dispersed inside the water column, but it's near the surface, and it goes down quite a few feet into the water column itself. But there's a higher density of plastic of all types, from containers, plastic containers floating around, all the way down to microscopic plastic and plastic fibers that are just kind of in the water column there, floating around and into the water column, right? And that's the Great Atlantic Garbage Patch. And it's called great because of its size, not because if it's fantastic. It's actually a fantastic pollution of the North Pacific, the Pacific Garbage Patch, right? So that's formed mostly because of this gyre. It's of concern because as plastic breaks down little by little, mostly from the exposure to UV at the atmosphere, and also the creatures that grow in it, mostly barnacles and so forth, they break it down over decades and centuries, and eventually it becomes microplastic, and then that microplastic is just suspended in the water column, and it gets into animals' filter feeders. filter feeders, mollusks and other seashell, things like that, even the plankton, the zooplankton. And then when other animals eat those filter feeders, it accumulates into the body of the other animals. And remember the pyramid, the food pyramid by biomass, 10-to-1 ratio. So that plastic keeps concentrating inside the animals, in the animal tissue, at a 10-to-1 ratio. And eventually, when we get to the large fish that we eat, then that fish, little by little, is getting an increasing amount of these microplastics in their tissue. And we're eating that. And there's some evidence that is coming out, this is just being studied now, that that microplastic in our own system may cause an immune reaction. It may irritate our own tissue because it's foreign particles after all. It may cause immune reaction and so forth. So there's an increasing concern for microplastics in the water system. I'll talk about microplastics further down the line in future lectures in this course, because there are other sources of that microplastic that is running off from the surface of the earth, from runoff of pollution, okay? So it's a concern. Anyway, that's another gyre. There's another gyre in the South Pacific that rotates, again, counterclockwise. So that's 4 of them: North Atlantic, South Atlantic, North Pacific, South Pacific. And then in the Southern Hemisphere, there is one more gyre that is not in the Northern Hemisphere, and it is the Indian Ocean gyre. And here you have it. The Indian Ocean gyre, just south of India, even though India itself is in the Northern Hemisphere, yet south of the equator, there is essentially the Indian Ocean down there, right? And that is causing another gyre. That doesn't happen in the Northern Hemisphere because there is landmass in the Northern Hemisphere. You got essentially India and Asia. And so there are mini gyres up there, but not the big gyre that happens in the Indian Ocean. So that's the 5th one there. And again, the rotation is always counterclockwise in the Southern Hemisphere, right? Driven by the Coriolis effect, in other words, the spin of the Earth. All right, these ocean currents also affect the wind pattern, and especially with humidity with regards to water evaporating from the ocean and forming the cloud formation, whether it's warm water or cold water, has a different effect on the atmosphere, on the troposphere column of air there with regards to humidity. And that can also be a factor in weather and over long range, eventually into climate. Okay, let's shift a little bit into solid water, natural solid water on Earth. This is one of the just empirical evidence of why we are not in a full-blown interglacial period, but we're somewhere in between because we still have solid water on Earth, natural solid water, what we call ice, basically the ice caps of the 2 poles. That's where most of the ice is on Earth. There's also ice in glaciers, but when you compare the volume of glaciers, of all the glaciers of the world, compared to the ice caps, the glaciers really are negligible by volume, simply solid water ice, okay? So the most significant ice masses on Earth are obviously the 2 poles, the 2 caps. But those 2 caps vary, they're very different one from the other as far as the ice is concerned, because the ice mass on the poles, of the North Pole, where there are 2 main chunks, if you will, 2 main chunks of ice, 2 main caps, the North Pole itself, the ice on the North Pole, and then there's Greenland. Here's Greenland, and is dotted, the Arctic Circle is dotted. So you can see the North Pole ice itself, and then Greenland. There's a big contrast between these 2 because whereas Greenland, the ice glacier is sitting on top of Greenland Island, right? On top of continents, on top of crust. The North Pole, the ice cap of the North Pole is not sitting on top of any continent, all right? There's liquid water underneath. There's the Arctic Ocean underneath. And that was finally verified that there is no continent underneath, precisely with the submarine, the Nautilus, which was the first nuclear submarine, okay? The Nautilus back in 1958. And why was it important that it be nuclear? Because diesel, the previous category of submarines, the previous class of submarines, whether it was US or other parts of the world, other nations, they were run by diesel, right? And so they could not hold enough diesel fuel to make a voyage across the Arctic Ocean from the Atlantic to the Pacific, or vice versa, from the Pacific to the Atlantic. I don't know how long it takes in time, but the previous class of submarines could not hold enough fuel to make that trip across, all right, that voyage. But once we went nuclear, then the amount of energy stored there is far greater, and these submarines can literally stay below the surface for months at a time, literally for months at a time, all right? And so the Nautilus was the first one to make the voyage. I don't know if it was from the Atlantic or to the Pacific or vice versa. I suspect it was from the Atlantic to the Pacific. Anyway, we have bases, naval bases on both coasts, right? And it went clear through underneath the North Pole, all right, from side to side, thus demonstrating definitively that there is no continent underneath the North Pole. So that's literally an ice, a chunk of ice floating, an ice cube that is floating, a huge ice cube that is floating on the North Cap, okay? Now, at some points, depending on the season, if it's winter or summer, it would be attached to segments of the crust up here, whether it's Siberia on the Asian side, or Canada, or even Greenland, if it's on this side of the Atlantic, right? But basically, there's some points of attachment there, but it does flow back and forth. Different from the South Pole, the South Pole, which is essentially a continent, Antarctica, and that has an ice cap on top of it, all right? But this is basically a continent, a frozen continent, all right? So it is solid underneath, and therefore it's a different dynamic. But these two poles are holding a relatively large amount of water, mostly fresh water, right? Because it's ice. And if they were to melt, if these poles were to melt, and we would have essentially no frozen water, natural frozen water on Earth, right? The sea could rise maybe 100 to 200 feet, all right? As it has happened in the past. And so there goes the peninsula of Florida, right? And we would, that's why we are ground zero, number one, for the 50 states, we are ground zero for sea level rise in the peninsula of Florida, because as the sea level rises, the peninsula would eventually disappear underwater, okay? Okay, so the ice, the significant amount of fresh water is being held in the polar regions today, so that we have the present coastline. Later, in later lectures, I will show you some models moving forward from our current coastline. If the poles were to melt eventually, what the coastline would look like in these projections as the sea level would rise. And of course, we would get less and less coastline, or the receding coastline inland. With these models, it's interesting to look at them and are concerned, right? All right, let's talk a little bit about glacial periods and interglacial periods and ebb and flow of these glaciers. Here is an example of a glacier that is flowing out to, I don't know if this is maybe the coast of, I don't know which coast this is, but essentially you can see that a glacier is pretty much like a river, but it's ice, all right? So it's solid water, but it does flow slowly, flows down river, downstream. And what is pushing this glacier down is accumulation of ice on the top of the glacier that is pushing down by gravity. All right? So glaciers do flow, and in fact, over long periods of time, they ebb and flow back and forth, and you can see that it grinds everything on its way until it reaches bare rock, and it even grinds that down. I think I've told you before that the Great Lakes were carved out from glaciers. The Great Lakes were carved out from glaciers. Wish I could get a map. How can I quickly get a map? Here, maybe. More or less. So it looks more or less with a little imagination like fingers of a hand that are pointing downward. Okay. The most significant one is Lake Michigan, I believe is this one. There are 5 Great Lakes up there between the US and Canada. And they were carved out by glaciers moving back and forth over hundreds of thousands of years. Okay? And they are, to this day, some of the deepest lakes in the world. The Great Lakes, they're V-shaped and they go very, very deeply. And they were carved out by glaciers moving back and forth. Interestingly, during the last glacial period, so the peninsula of Florida has never been covered by glaciers. And the last glacial period went about halfway here down. But that means that all this that you see green, the vegetation kept being pushed down by the glacier as it was moving over centuries and millennia, and also the animal species. So many of these animals and plants came down into the peninsula. And this is like an actual funnel, right? Including the slash pines that I've been talking about off and on in the program, what we call Dade County slash pine. These are conifers. What are conifers doing in a subtropical environment? Well, they were being literally pushed down. In other words, as the glacier was advancing slowly down toward the equator, seedlings that were germinating ahead of the glacier kept moving forward and forward and forward until that forest literally came all the way down. Also keep in mind that with glaciers, of course, we're going toward a winterization of the earth, meaning the climate is colder and colder. Even if we didn't have ice, we did have the cold climate, and therefore it was more suitable for animals and plants that are adapted to the cold, meaning mammals on the animal side and conifers on the plant side, right? And so these are the only conifers that adapted eventually when the glaciers receded, adapted to a warmer climate, to what we have today, a subtropical climate. So it's rare, very rare to see conifers, pine trees, growing in a subtropical climate, right? And so when you see pines and palms together, that should be a reason for pause. People in the know, people who know their vegetation, should understand, will right away understand that that's a rare sight to see pines and palms together, because the palm is a tropical plant that tolerates very little, practically no cold. And you can see, even as you go north on the peninsula of Florida, by the time you get to Georgia, basically the palms disappear, all right, because they don't tolerate any degree of cold weather. They literally freeze and they don't tolerate the cold weather. Whereas pines are extremely tolerant to cold, to the point that they can tolerate ice and snow on top of them for months at a time. all right, and freezing conditions. So when you see pine and palm growing together, you can bet your bottom dollar that of the two, the one that has adapted is the pine, okay? Has adapted to the subtropical environment. And so it's a unique, rare site. And that's another reason why we're trying to preserve this pine forest that we have here at St. Thomas University. Okay, back to the cycle. Let's look at this and project it in a time frame. Here, of course, you can see that this glacier has receded and has left the bottom of the glacier exposed, totally eroded away down to the bare rock, all right? And of course, the hardest rock is gonna be granite, and so it will wear out all of the other igneous rock and sedimentary rock and whatever other type of rock is on top of it, down to the granite or the hardest rock. And all that sediment is going to, the rubbles and all that are going to add to the grinding and the erosion motion of that glacier, all right? And that's all going to be dumped down river, downstream into the ocean or whatever, maybe a lake. Those lakes, by the way, that form way high up on the mountains, they're called cirque lakes, and typically they are the beginning of rivers that will flow down down the mountainside. You get those in the Rocky Mountains, for example. They're beautiful camping sites up there. Anyway, let me look at this because this scale here, this graph, right, goes back only about 500,000 years, only 500,000. Remember the age of the Earth, 4.5 billion years, okay? So really 500,000 years is not even 1 million years back. And we have evidence from the geology of places on Earth that there have been at least 4 major glacier and interglacial periods, all right? So if we were to draw a curve, an average curve, a slope of these temperatures, the slope will describe 4 major peaks and 4 major troughs. And this is where we are today at about 30, this is temperature, these are not degrees latitude, all right? This is temperature, global temperature, average global temperature of the Earth. So we are certainly above freezing, all right, at this comfortable temperature of 30 degrees centigrade. Remember, body temperature, 37 degrees, right? So this equates to about, what, high 70s, or what is 30 degrees? Someone want to look it up in Fahrenheit? I forget. Well, oh, this is Fahrenheit, I'm sorry, yes. Sorry, okay, so this is freezing, yes. Sorry about that, sorry. Thank you. Yeah, this is Fahrenheit, so this is freezing. Right, so below will be glacial periods, above are interglacial periods. Okay, so you see the peaks coming up, and the troughs are full glacial, 4 major glacial periods, and 5 interglacial, but it's anybody's call which way we're heading because we're hovering just above freezing here for the past few centuries, all right? Maybe a few thousand years. We don't know where this is going. This could go up into a tropicalized Earth, or it could go down into a winterized Earth. We don't know, okay? But of course, when we add the anthropogenic issue of increasing CO2, which is increasing atmospheric temperature, the expectation and the models is that this is going up, this temperature going up rather fast. So due to the anthropogenic factor, it could be that we're heading toward a tropicalized Earth. Getting a little bit ahead of myself, but basically it's important to understand these glacial periods, maximum and minimum, all right? Because there's a periodicity. What I'm trying to say with this is really that there's a certain periodicity to the slope of this line. Right? But it's not too regular, but there seems to be a cycling here, a natural cycling, because certainly just going back 1,000 years, right? It's before industrialization, before burning fossil fuels in a significant way or in a large quantity. And so just a mere 1,000 years ago, whatever cycling was happening on the Earth, we had nothing to do with that. And we can see that the Earth has shifted back and forth from a tropicalized Earth to a winterized Earth, where mostly the land masses on the northern hemisphere, which is where the land masses are being covered with ice. Again, we're talking 1 to 2 miles of ice on top of us, to the alternative, which would be the sea level rise of 100 to 200 feet of sea above us. All right, I'm talking about this lower part of the United States, the peninsula. Okay, so these are natural cycles of which we had nothing to do with as humans. It means that the Earth follows these cycles, and we don't know exactly where we're heading, but we do know that little by little, we are losing heat to the atmosphere, right? From through the crust, from the mantle. So that may have an effect also on these cycles or not. They're really complex cycles, and no one has figured out exactly what are all the factors that contribute to the cycling of glacier interglacial periods on Earth. We're just a couple of slides away, so let me go to this little site here, this Wikipedia site, because it may show, they had one had an active site in it. Yeah, okay. All right, so this is just more detail on the graphs. Go back. It's one of these that showed, sorry, had a little motion. Anyone know how to go back to the Wikipedia site? Wiki Ice Age, maybe. Bear with me for a moment. I'm just mumbling here. Maybe easier if I put Ice Age, Wikipedia. This, maybe. Okay. No. It was an active site that had, it cycled around. It showed the ice melting and accumulating. Well, anyway, one thing I do want to say about the these ice ages. How do we get this information? Because obviously the thermometer has not been around for so long, right? Going back thousands of years. So it's indirect measurement. Indirect measurement, mostly ice cores that are done on glaciers or the Antarctic or the North Pole, drilling through and getting these long, long ice cores. And sometimes what scientists explore is little bubbles. Okay, these are ice cores, you can see. pretty long, and they're all segmented. So they cut sections, and then they look at the amount of CO2, sometimes trapped, CO2 trapped inside the bubbles, concentration, or they look at sediment particles, which could be ash, for example, from volcanic explosions and so forth. So you see the banding here. This could be, I'm just guessing, but this could be possibly volcanic activity, high volcanic activity on the Earth that has deposited the ash throughout the surface of the Earth, including the poles. And so these are very informative, these ice cores, as they're being studied, all right? And they tell us, see, you can see the pattern of banding, which is implying some cycling. And many of these cores are kept either in the North Pole or the South Pole, which will be freezing temperatures, and that's why it's preserved there. This is an example of a little core where you can see it's very porous. It has a lot of little trapped bubbles of air, and they can measure, scientists can measure with very precise instrumentation the amount of CO2 inside those bubbles, the concentration, to see what ppm it had, right? 100, 200, 300, 400 ppm. And they can then estimate the temperature of the Earth at that time from the CO2 concentration. This is actually a cave where they walk in, scientists walk in, and they can see the layers and the cores that are being studied in here. This is a cave of ice. I forget if it's in, oh, here it is, Antarctic. In Antarctica. All right, so a lot of experimentation going on in the poles here because of the melting poles that is going on right now. So that's how these models are estimated, but they're pretty accurate, okay? All right. Couple more slides. First, the distribution of water in the world, because what we want to get to is this fraction of 1% here. All right, this is a 1% of a 1%. So if all of the water on Earth represented 100% of water, all right, most of that, the vast majority of water on Earth, natural water, is salt water, is the oceans. Only about 3% of all water on Earth, natural water, is fresh water. Now that 3% includes all of the fresh water. So we go into the next little hypothetical pool here on the diagram. So all of the fresh water, that 3%, is taken up mostly by the ice caps and glaciers. All right, but the glaciers, I can tell you, is negligible compared to the ice caps. So the vast majority of fresh water on Earth is actually solid. Think about that for a moment. The vast majority of fresh water on Earth, and it's only 3% of it, is solid, which means it's not really available. All right, except for studying it or melting it, but it's solid in the ice caps. And most of that is going to be in Antarctica again. So that represents about 79, rounded up to 80%. Okay, so 4/5 of the water on Earth is unavailable, fresh water. All right, now, of that fresh water, about 80%, 79% is in the ice caps, not available. About 20% is groundwater meaning underground, like the Biscayne Aquifer, for example, that is the one that feeds our water, okay? But this groundwater typically is below, fairly deep below the surface. And of course, not all groundwater is accessible to us because some of it is fairly deep or in areas where we just cannot get to it because the crust is too thick. So surface water that is accessible is only 1% of that. So we're talking about 1% of the total amount of water, 1% of the 3%. The next layer, the next layer down is this third hypothetical pool here for purpose of diagram, or actually these are pie charts. Of that 1% of fresh water that is accessible on the surface of the crust of the earth, about half of that is lakes, and the other half is mostly moisture, so it's not available. Moisture in soil, trapped in moisture, about 40% of it, all right? So almost the other half. And then that little fraction of the pie chart, 8% is water vapor in the atmosphere. So again, not available. 1% rivers. And finally, the last 1% of a 1% of a 3%, that is the water that is with living organisms that we're holding in our bodies, okay? In other words, where life occurs. So life occurs in the 1% of the 1% of the 3% of water on Earth. Very tiny fraction that is being actually taken up for life. So it's a very modest, tiny amount of the water on Earth that is being used for maintaining life, okay? And that's of all the living organisms on Earth. Then we could fraction that to an even smaller amount, much smaller amount, for just the human bodies, okay? So we would look at the biomass, the total biomass on Earth, and then we would measure the biomass of humans. We can take the average biomass of one human and multiply 8 times 8 billion approximately, and that will give us the total biomass of all humans on Earth. And then we can figure out what percentage of this 1% belongs to human metabolism, to keeping humans alive. And that essentially is the amount of water that we need available for staying alive, which is a very, very tiny amount. And yet, without that much water, there will be no life on Earth, no human life either. Okay? So really, all we need is a very, very small amount of the total water on Earth. But without that very tiny amount, there is no life. It's a little bit like the percentage of oxygen. We need a much larger percent of oxygen in the atmosphere, for example, that we need of water from the Earth, simply because of the vast amount that there is. But most of it is taken up by the oceans. All right. Finally, I want to wrap it up just like in the previous lectures, ending with the human factor here and natural rights, beginning with natural rights. And then in the second half of this course, we'll look at natural responsibilities, right? Because one thing is to talk about rights, and we can talk about rights all day long until we're blue in the face. But if we don't talk about responsibilities, then there's no point about the rights, because if we don't defend the rights with responsibilities or duties, then those rights are going to go away, okay? So we have, just like we have a natural right to live somewhere on Earth, with regards to the geosphere, we have to have a footprint somewhere. We try to make an eco-friendly footprint and not take excessive amounts of land on which to live and do agriculture and so forth, but we have to live somewhere. So we have a natural right to a footprint on Earth. We also have a natural right to air, because without air, we die. And so we also have a natural right to water, to fresh water, and to drinking water. So one thing is to have a natural right to water, for example, to shower, doesn't need to be drinking water necessarily, all right? But fresh water that is potable water, drinking water, that's a different story, because many of the freshwater sources of the world are sadly contaminated. Not for us who are in well-being, but in other parts of the world, large amounts of people in the world don't have access. I think it's about 50% of the population of the world doesn't really have direct access to potable water like we have, drinking water. We open the faucet and it's drinking water. People are buying plastic bottles all the time, plastic bottles of water. I can tell you that I have been living in Miami over 50 years. I've lived in many parts of the Dade County, the southern part, the northern part, east, west, all over the place. I've always drank tap water. And I'm still here, healthy, hasn't killed me, all right? And I feel great, so good. Well, you'll see in the health club, but I've never had a problem with drinking the tap water anywhere in the city of Miami or the Dade County. And I highly recommend it so that we get away from buying plastics and single-use plastic water, which is a total disaster for the environment, okay? Because this plastic bottle in the environment will last thousands and thousands of years. Well, we don't know exactly how long it lasts because we haven't had plastic for thousands of years, but it's very hard to break down. And therefore, recycle your plastic bottles and just drink tap water like I do all the time. It's a big concern, this whole issue of water. It's an increasing concern. I can tell you from the Catholic perspective, every modern pope has talked about water and the natural right to access to water. There's not a religious right, okay, like practicing our faith. This is a natural right. So even non-religious people, non-Catholics, non-Christians, non-believers also have a right to natural water, to clean water and to drinking water. So it is on behalf of all peoples of the world. Every pope, we say modern pope since the Second Vatican Council. There's a photograph of Pope Paul VI, who brought the Vatican Council to conclusion about 60 years ago in 1960s, all right? I was a little kid back then, I'm that ancient, that I remember the Vatican Council as a child. And here with him, there's a young cardinal called Carolus Wojtyla, was the Cardinal of Krakow at that time in Poland, who eventually became John Paul II, okay? Here's with one of his best friends, Mother Teresa of Calcutta. They were both, well, he was younger than her, for sure. But every modern pope has talked about the right to water and the urgent need for water for the world. Here's Pope Benedict having a conversation with Pope Francis. This is an interesting photograph because we've got two popes at a time. Of course, one of them has to be retired. Otherwise, we have a pope and an anti-pope going on. So this is when Pope Benedict just retired and Pope Francis came to visit him. And they're having that this little chat. Pope Francis came to visit, retired. Benedict had just retired. I think he was at the retirement home of Castel Gandolfo for the popes. Their summer residence outside of the city of Rome. Here's Pope Francis actually giving a talk at a conference on water at the Vatican, an international conference on water. This was about 3 years ago. Oh yeah, well, there it is. The Pontifical Academy of Sciences is a body that was instituted maybe a century ago. It goes way back. I don't know exactly when. Let me look it up. Pontifical Academy of Sciences. No, of Science. Here it is. So the Vatican has a number of offices or departments, if you will, that are consultatory to the Pope, all right? So the Pope really is not isolated in a bubble by any stretch of the imagination. If governors of nations and presidents and prime ministers and kings and queens and so forth, monarchs have access to information and they have their peritae, they have their advisors, all right, on many, many issues because these world leaders, they're not experts in every field. Sometimes world leaders are also doctors or medical doctors or lawyers or engineers and whatnot, but typically they're not, all right? And so they depend on counsel from experts, and they have many, many experts that counsel them on many issues, including issues of life and science and nature and technology and so forth. Well, of all the world leaders that you can think of, the one I can guarantee you has the most access to most experts throughout the world is the Pope, all right, whatever Pope it is. And so it started with these different departments of the Pope, of the Vatican, that we call academies, or sometimes there are dicasteries and other names, but the academy is typical of the scientific ones, all right? So this Pontifical Academy for Science, and the fact that it's pontifical is just a reference that it belongs to the Vatican. And in these pontifical academies, you have experts from all over the world, and they're not necessarily Catholic or Christian or even religious. Sometimes you have atheists. The one condition for these, look at Steve Hawkins, for example, who was not a, in fact, he started out as a believer, and at the end of his life, he was an atheist. He denied the existence of God. So these are all world scientists, world-renowned. And the one common characteristic of all these experts, scientists, is that they have to be top of the line in their particular fields, all right, in their scientific fields. And so, here's some names, for example. No, well, I don't recognize any of these, but these are famous scientists throughout the world. And I just wanted to see when it was founded and all that, but one of the popes founded this Pontifical Academy of Sciences, and it goes back decades and decades. And so these are experts from all over the world that come and counsel the Pope on scientific issues, all right? Astronomy, you name it. So here he is addressing, whenever the Pontifical Academy for Sciences goes into session, all right? Then the Pope typically gives an address, and this one was on the right to water, the human right to water back in 2017. And you can see from the date that it was happening right when I was teaching this course back 4 years ago. So I started the program 5 years ago. So this was in the cohort, in the first cohort, because the program started 5 years ago. You folks are the 5th cohort, right? And it started in 2016. So this program started in 2016, but in the fall of 2016. So really by February, which was this course 5 years ago, it was the first cohort moving through, and providentially, it was this conference on the human right to water. The Pope gave an address at that time, and I sent you, it was just a one pager, all right? So I sent you that address that they gave, the papal address, which is now historical, of the urgency of the need for people of the world to have access to drinking water, all right, as a human right. So this is a human right that, for example, the United Nations is very concerned with and so forth, and we align ourselves with the concern of the world providing water, access to clean drinking water to the people of the world. Then, providentially, what just came out from the Vatican was a document, because this has been going in increasing urgency to get water, fresh water and drinking water to the peoples of the world, considering that about half of them don't have, 4 billion people don't have access to drinking water directly. They depend on wells like this. Some kids spend their day, their lifetime, their childhood going to the river or to the water source, bringing water home for it to be boiled so it can be drunk and used for washing and so forth. And so they don't have time to go to school because they have to go fetch water. and water is very heavy, so they have to make that trip several times a day, maybe just carrying 1 or 2 gallons on their bodies. So it's a pretty dramatic thing, especially in the southern hemisphere in general. All right. So when we get out of North America and Europe, there are drastic conditions out there, all the way across Latin America, Africa, and Asia. This document just came out providentially. Here we are also in the environmental bioethics course talking about water. And here, sorry, it's got date of March 2020. However, oh yeah, because it was sent to me last year. I'm sorry. I got confused. Anyway, this document came out last year. It's on water. It's from the Vatican. All right. It's a very beautiful document. You can read it in any language that you want. It's in English and Spanish, Italian, etc., etc. But it's called Aqua Fons Vitae. So I should incorporate it. I'm going to send you an updated version of the PowerPoint so that it includes at least the link to this document, because it's really worthwhile reading this document. It's a beautiful document on the urgency of preserving the oceans. It obviously speaks very strongly against contamination and pollution and so forth. And it also gives a lot of guideline of what to do to preserve the water on Earth, the natural water of Earth, whether it's drinking water or the oceans for the ecosystem. Okay, so these are all consequences coming out of Laudato Si, the encyclical that Pope Francis wrote in 2015, one of the motivators that I had precisely for launching this Masters in Bioethics. And the 2 international conferences that we've had, not 1, but 2 international conferences on climate, nature, and society. I'll talk a little bit more about those conferences as we go along in the course, but we've had 2 international conferences here in St. Thomas University on climate, nature, and society. So a lot to do with the environment, all right, and preserving the natural environment. Okay. So with this lecture, we have covered now the 3 major spheres of Earth, the geosphere, the atmosphere, and the hydrosphere. And this is basically background. It's based mostly on the science of it, so that moving forward, we'll be looking more and more about the human impact on these 3 spheres, because together, those 3 spheres, these are the basic requirement for holding life on Earth, the biosphere or the ecosphere, excuse me, and that's where ourselves included into the biosphere as one of the millions of species that live here on Earth, all right? So it behooves us to preserve it, but in order to preserve it, we need to understand it to some degree to know what we're doing and what we're doing right and what we're doing wrong. All right, so these 3 first lectures have been just kind of introducing the topic, mostly of the abiotic factors, if you will, of the holding the biosphere to be able to hold life on Earth. Excuse me. All right, so I'm going to stop here. Just a little bit under 12:30. So again, questions, comments, anything? Nothing? All right, then I'm going to...
I actually have a question.
Okay, yes, sure.
Are we going to be speaking about the Flint, Michigan water incident, or, you know, situations like that?
Right, we can look at it. There are various areas of contamination that have happened on Earth and in the United States, so we can address them. Some of them are a little controversial because some of the information that was put out originally was either exaggerated or falsified. For example, the thing that you mentioned, I want to research a little bit more, but basically it was proved that what was coming out of those faucets was gas, but it wasn't necessarily produced by the fracking. I'll talk about fracking later on in the lecture also. It turned out that there were natural bacteria that were accumulating and were producing essentially methane, which is a flammable gas. All right. And so people were associating that with fracking originally, but then it turned out that it was not gas coming out from fracking, but actually from bacteria that were producing that methane. But I'm glad you bring it up because I'll address it a little further, like I mentioned in the lectures when I talk about fossil fuels and the shift from fossil fuels to alternative energy sources. Okay.
Got it. Thank you.
Okay. Thank you, Chris. Anything else?
Yes. At the beginning of the handout, there is a statement for inhomogeneous accretions. I don't know what that term comes.
Yes. Thank you. Thank you for bringing that up. Let me see if I have access quickly here. So there are three types of mixtures. Remember that we had homogeneous mixtures and heterogeneous mixtures, but that was for the sake of simplicity. There's actually an in-between mixture that is called inhomogeneous. Wouldn't you know it? I don't have that PowerPoint here, but give me a minute and I'll find it through the emails. I just need to get into here and then do Geosphere for a moment. Just want to raise, look at that, the marvels of technology. When it works, it's great. I'm looking for a little slide that actually portrays inhomogeneous mixture or accretion, because like the saying goes, a picture is worth what? 1,000 words, right? So it's a picture is worth PPT words. One PPT word. Okay, here's, all right, the layers. It has to do with the layers of Earth. Maybe this one is one. All right, here we go. Yeah, there it is. Inhomogeneous accretion. So inhomogeneous means that as a whole, it is not homogeneous, but it's not heterogeneous either. It's not a total mixture of layers, but within each layer is homogeneous. And that's what it means. Accretion is the formation of the Earth, right? And so it has these 5 layers or 3 main layers and 2 sub-layers. We have the core, which is nickel iron, that is solid, right? And that forms first, and then the mantle forms next, and then finally the crust forms last. And then eventually, with more time, the inner and middle layers become further differentiated into inner and outer core. Remember, the inner core being solid, the outer core being liquid. And then the mantle, also the upper and lower mantle, become differentiated again. All right. So this further differentiation ends up making what is called an inhomogeneous accretion. All right. In other words, that is not heterogeneous totally, and it's not totally homogeneous either, but it has these layers that develop over time, and that process is called inhomogeneous, because within each layer, you can see it this way, within each layer, there is homogeneity. But there are 5 different layers as a whole, and each layer has a different density, obviously, okay? All right, so that's inhomogeneous, and its accretion is a reference to the formation of the Earth. as it was getting first bombarded and also as it developed the core. Now this core is going to exert a gravitational pull. So it's going to invite, if you will, pull in more debris that was flying around, increasing its mass. It's increasing its mass gradually until we have the current Earth, and this is actually a photograph of the current Earth, fully differentiated. All right. Anything else? All right. Then, if there's nothing else, I'm going to close the recording, and we'll meet again next Saturday, God willing. All right. So, everybody have a great week. We'll see you next week.
Thank you, Professor. Have a good one, guys.
Thank you. All the best. Bye.
Thank you.
Thank you.
Bye, thank you.